All right, we will now use this system to discover the eigenvalue algorithm together. So let's take a look at this system and notice what appears to be bad news at first. And that is we have two equations and three unknowns, x, y, and lambda. But then we realize maybe it's not necessarily bad news, because after all, we're not looking for a unique solution. We know exactly what happens when you try to find eigenvalues and eigenvectors over linear transformation. We usually get several different values for lambda, sometimes as many as the dimension of the space. So here we expect at most 2, because we're in a two-dimensional space, R2. And then x and y are even less unique. When we find one vector xy, then any multiple of that vector also satisfies the equations. It's an entire eigenspace. So that's the kind of lack of uniqueness that we find when we're dealing with null spaces. If you have a vector in the null space, any multiple of that vector is also in the null space. So maybe that's the sort of thing we're looking for here. And sometimes there's even less uniqueness. Sometimes we find that corresponding to the same value of lambda, there is a two-dimensional space of vectors that are eigenvectors for that lambda. So that's the sort of thing we may find here as well. And that's also the sort of thing we sometimes find in null spaces. Null spaces are not necessarily one-dimensional. Sometimes they're two-dimensional and even higher dimensional. So we should be happy that we have more unknowns than equations, because we're looking for non-unique solutions. Of course, these are non-unique solutions in a very peculiar way. Lambda takes on discrete number of solutions, discrete number of values, maybe 1, 2, or in this case at most 2, but in higher dimensions up to the number of dimensions. And x and y are continuously non-unique, meaning any multiple of a solution is another solution. Sometimes even a linear combination of different solutions is a solution. So it's a very unusual sort of behavior. But then again, this is an unusual sort of system. So I think it's intriguing to find how by manipulating this system, we can end up with anything where lambda takes on just a couple different values and x and y are continuously non-unique, if you can put it that way. So let's just start analyzing the system, and that will present itself in a very beautiful and maybe unexpected way. But of course, the simple system serves as blueprint for many more, much more complicated problems. All right. So this is not a linear system of equations. That's important to realize. This is not ax equals b. Ax equals b means the right-hand side is known. Here we have unknowns, in fact all three unknowns hanging out on the right-hand side. So it would do us no good to multiply this whole system by A inverse on both sides, because that would give us x and y in terms of x and y and lambda. So it's a circuitous type of expression, not helpful at all. It would even not help us to express x and y in terms of lambda, because lambda is just another unknown. If we knew lambda, it would be a totally different story, but we don't. So we have to acknowledge that this is not a linear system of equations. This is a new type of system. It's not ax equals b, it's ax equals lambda x. So to begin the analysis, let's rewrite these equations as something more familiar. Let's just write them as indeed a system of equations, where the first equation reads 2x plus y equals lambda x. And then maybe our algebraic intuition will kick in, and we'll start getting ideas of what we can do next. All right, so because we're now going to be dealing with individual equations, I'm going to draw a square bracket. I don't think, curly bracket, I don't need that much space, so I can go to the right a little bit. And the first equation reads, like I said, 2x plus y, 2x plus y equals lambda x, equals lambda x, perfect fit. And the second equation reads x plus 2y equals lambda y, x plus 2y equals lambda y. Right? So this is an example where thinking of the system in block terms, where you think of this matrix as an indivisible whole, and so are these objects, is not really helpful. So we're doing what we haven't done in a while. Go back to looking at a matrix as a collection of entries and even as two equations, right? So we've been discouraging this approach, but now that we're encountering a brand new system, the kind of system we've never seen before, right? We're a little bit desperate. So we're trying to go back to a format where we might get some kind of ideas on what to do next. And in fact, we do. There is a temptation to maybe move all of the unknowns to the left-hand side. That actually proves productive. And then group the unknowns to the extent possible. So let's see what happens. So here's the suggestion. Bring these unknowns to the left-hand side, and then factor out x in the first equation and factor out y in the second equation. And then we'll see what sort of thing we're looking at. And it will actually kind of reveal the answer. So here's the system that we get on the left-hand side. I'm out of the shot now, but you see what I'm writing. So the first equation becomes 2 minus lambda times x plus y equals 0. Okay? And the second equation becomes x plus 2 minus lambda y equals 0. All right? What are we looking at here? So it's still not a linear equation because we have three unknowns, x, y, and lambda, and it's linear in x, it's linear in y, but as a totality of variables, it's not linear because we have lambda times x. So maybe it wasn't particularly helpful, or maybe it was. Let's now break up the variables and try to think of this as a linear system, because by now we've become quite good at solving linear systems, and I'm kind of seeing linear algebra structure, linear system structure in this, just in terms of the variables x and y. This is a linear system. It's not a linear system with known coefficients, but it's close to the sort of linear system we're familiar with. It's just that the coefficients have an unknown in them. So something unusual is still going on. But now at least let's rewrite it as ax equals b, where A is not a matrix with all the coefficients known, but writing this in the form we're familiar with from the linear systems point of view will actually prove helpful. So I don't need parentheses here. 2 minus lambda, 1, 2 minus lambda. All right, excuse me. Times xy equals 0. 0, 0, the column of zeros. All right, so actually now we're getting somewhere. Here's what we're getting. So what appears on the board now is the question of the null space. It's the question of the null space for this matrix. It's just like the original matrix, except on the diagonal we subtracted lambda through this manipulation of individual equations. But now we're back to thinking in terms of the whole thing in terms of block structures, whole indivisible types of objects. So we know how to solve the null space problem, which is what this is. Except we know that most of the time the answer is boring when the matrix is 2 by 2. If these columns are linearly independent, then the only solution is the trivial solution, 2 zeros, 0, 0. And that's just not the sort of thing we'll look for when we look for eigenvectors. Remember, an eigenvector is necessarily a non-zero vector. So now we're really getting somewhere. So for most values of lambda, in fact for all values of lambda that would make this two columns linearly independent, in other words, would make this matrix invertible or full rank, whatever you want to call it, use any synonym you want, there is no solution. There is no interesting solution. There's only the trivial solution, and that's not the sort of thing we're looking for. And we have just arrived at the condition that quote-unquote discretizes lambda, that gives lambda those finitely many values, those finitely many special values that make it possible for this system to have a solution with non-trivial x and y. And the solution and that condition in words is that lambda needs to have that special value or those special values that would make these columns linearly dependent. So that's the key. Once we've arrived at this point, we now realize we've pretty much got this problem cornered. We're now looking for those special values of lambda that make this matrix singular. In other words, make the columns linearly dependent. Okay? And then once we find lambda like that, corresponding x and y are simply the null space of this matrix with those special values of lambda plugged in. One small problem. So let's summarize the good news first. The good news is that we now know what lambda and x and y to look for and the properties that they have. The bad news is that right now we have this equation solved with words. Words are not very helpful when you need to get the actual values. We need equations. So instead of saying, well, we need that special value of lambda that would make this matrix singular or would make the columns linearly dependent, right, is not very helpful. Maybe in this case, we can guess those special values of lambda. How about lambda equals 1? That would make it 1, 1, 1, 1. So that's one of them, but we guessed it. We're looking for something robust. While we're at it, let's guess the other one. How about 3? That would make it minus 1, 1, minus 1. This column would be minus 1 times the first column, and once again, linearly dependent columns. And there wouldn't be any other values of lambda, but how can we be sure? And then how could we solve a system like this robustly, even if we couldn't guess the solutions? Determinants to the rescue. We know that the determinant of a singular matrix equals 0. And since we're looking for lambdas that would make this matrix singular, so that we can have an interesting non-trivial null space here, we're looking for lambdas that would make the determinant of this matrix equal 0. And that's the beauty of determinants. They turn words into equations. And equations we know what to do with. So what I'm going to do right now is erase everything that's non-essential. Start with the equation that states the determinant of this matrix equals 0. Discover the algebraic equation that it leads to. Solve that equation. And then we'll have our eigenvalues. All right, so we're looking for the special values of lambda that would make this determinant equal 0. So let me step out of the shot and evaluate this determinant, which of course is this entry times this entry, which is 2 minus lambda squared, minus this entry times this entry, which is minus 1. A simple 2 by 2 determinant. Expanding this, we get lambda squared minus 4 lambda plus 4 minus 1, so plus 3. And of course we're looking for the values of lambda that equals 0. So we have a simple quadratic equation which we can easily solve. This polynomial is known as the characteristic polynomial. When you equate it to 0, you get the characteristic equation. And its roots are of course the eigenvalues of the matrix, also known as the characteristic values. But this also signals a little bit of trouble, because what if we get a cubic equation in the 3 by 3 case? That's a little harder to solve. And fourth order, fifth order, higher order algebraic equations, polynomial equations, for which we don't even have formulas for solving. So how would you solve those equations? Perhaps on the computer, but there's definitely something to think about. Nothing to think about here, however, because we have a quadratic equation which we can easily solve. And of course the two roots of this quadratic equation are 1 and 3. 1 and 3, just as we guessed before, but now we have a robust way of getting those special eigenvalues without guessing, just by solving the quadratic equation that comes out of a pretty precisely specified algorithm. And so we have our two eigenvalues. We now have solved for one of the variables. It has one of two values. We're noticing discretization. Two discrete values of lambda satisfy this equation. They're those magical values of lambda that make this equation possible, in the sense that the null space that this asks us to find is non-trivial. And of course, this system being equivalent to this system, it will lead to eigenvectors that are non-trivial, which is the only kind of thing that eigenvectors can be. Zero eigenvectors don't count as eigenvectors. So we're almost there. We have discovered those special values of lambda. So we have discovered our eigenvalues. We now have to discover our eigenvectors. And you do those one at a time. You find first the one corresponding to lambda equals 1, and then the one corresponding to lambda equals 3, which we can do right here. Lambda equals 1, and just let me make sure I manage space well, right here is good. Lambda equals 3. Let's erase equals 0 to save some space. Must equal 0. That's for posterity. Must equal 0. Okay, the one corresponding to lambda equals 1. Well, it comes from this equation. What we need to do is plug in lambda equals 1 and determine the corresponding null space. Because the null space of this equation is the eigenspace of the equation we're interested in. So the question of eigenvalues has been reduced to the question of null spaces. So everything we've learned before is not going anywhere. We're back to our null spaces. We're back to relationships among columns. So all of that stuff that we learned will continue to be extremely valuable. Okay, so lambda equals 1, plug it in. You end up with 1, 1, 1, 1. And of course, the null space is alpha times 1 minus 1. But the tradition in eigenvalue problems is to not summarize the entire eigenspace, but to simply mention one of those eigenvectors, or in the case of multi-dimensional eigenspaces, you choose a basis for that eigenspace and you call those vectors your eigenvectors. That's just tradition. So so let's call this lambda 1 and this one lambda 2. So V1, the eigenvector corresponding to eigenvalue lambda equals 1, centering everything, V1 is 1, negative 1, or 2, negative 2, doesn't matter, choose one. I chose 1, negative 1. Now let's make sure that it actually satisfies the equation. Multiplying this matrix by 1, negative 1 becomes 1, negative 1. Indeed, 1 times the input. So we solved this problem correctly. All right, don't know if I made it better. All right, now let's switch to lambda 2 equals 3. So plugging in lambda 2 equals 3 here, we get negative 1. We get negative 1, 1, 1, negative 1. And the null space corresponding to this matrix is alpha 1, 1. And once again, following the tradition of eigenvalue problems, we write that V2 equals 1, 1. Let's see if this is the correct solution. Plugging in 1, 1 here produces 3, 3, which is indeed 3 times 1, 1. So we have solved the problem correctly. Now let us summarize the eigenvalue algorithm, and it is relatively straightforward. When you solve eigenvalue problems from this point on, you don't have to repeat all of the steps that we went through. Here's what you'll do. You'll start with a system. I can stand over here. You'll start with a system. You'll subtract lambda from the diagonal. Find the determinant of this matrix in terms of lambda, and equate that determinant to 0. That will be a quadratic equation in 2 by 2 cases, cubic equations in 3 by 3, and you're in trouble if it's 4 by 4, 5 by 5, and higher order systems. We'll talk what to do in those cases separately. You will solve that equation, and that will give you your eigenvalues. And once you have your eigenvalues, you subtract them from the diagonal individually. In other words, you plug them into this equation. And for the matrix that you get, you find the null space. And the basis for that null space is the corresponding eigenvectors. And if the matrix that you got here is not singular, if its columns are linearly independent, that means only one thing, that you computed the eigenvalues incorrectly, and then you have to go back and fix your error. And that completes the algorithm.